Hello everybody. So today we are going to discuss part 3 of Markov chain. This is the last in the series of lectures on Markov chain. So as usual we will follow the format that Sitsiklis does, and we will discuss that. So basically just a quick review. So what we had was that we looked at basically towards the end of lecture 2, what we saw was what was the nice Markov chain. So we saw what was a nice Markov chain, right? So basically nice Markov chains are the ones which have the property that after some time, okay, after some time, I mean perhaps the time is quite large, the probability that you find yourself, probability that you find in some state j, okay, so this number it settles into a steady state. This number settles into a steady state. So what that means mathematically is, so limit as n tends to infinity pxn equal to some state j, given that you started in x naught, which is at I, this is going to be pi j, okay, for these nice Markov chains. This is true for no matter which I you start in, okay. So this particular statement captures two things. One is the initial state is forgotten, right, because it doesn't depend on this. So we may as well write this, if you want, we can write this as pxn equal to j equal to pi j. Okay, so this thing, first thing is that initial state is forgotten. Okay, and the second thing is the thing that it settles into a steady state. Okay, it settles into a state. I mean the probability, or the probability settles into a number. So I should be a little more careful here. Probability that you find yourself in state j settles to a constant pi j. Okay, so these are the two features that a nice Markov chain has. And the what do we mean by nice, that also we saw. So basically nice Markov chains are the ones which have the property that they have a single recurrent class. Okay, so basically a case like there could be several transient classes. So transient classes are those where, you know, if you start at, let's say I1 is transient, it will be the transient class if once it goes to some state 2, there is no way to return back to it. So something like this. Okay, so then you can have some Markov chain like this, you know. And if you see carefully, once you go from 1 to 2, there is no way you can come back to 1. So 1 is a transient class. Okay, so recurrent classes are the ones where, you know, no matter where you go, there is always a way to come back to that class. Okay, and if there is a single bunch, all the recurrent classes are able to go from one of them to the other. So if they can reach from, so let me give you an example of what it means to say two recurrent classes. Suppose we have a Markov chain like this, you know, so from 1 you can either go to 3 or 2 or so there is I have to be careful, this has to be 4. So from 1 you can go to 2, and from 2 you either can go to 3 and you will always perpetually remain between 2 and 3, or you can go to 4 and you will perpetually remain at 4. Okay, so neither 4 or nor 2 or 3 is a recurrent class, a transient class, because, you know, from each of these class you always remain in the same class. Whereas there is no communication between 2 and 4. That is because this forms one recurrent class and this forms another recurrent class. Okay, so a nice Markov chain is one where there is only a single recurrent class. Okay, and then this is property number 1. Property number 2 that we saw is it should be aperiodic. Now whenever you are given a problem involving nice Markov chains, okay, which have these two desirable properties, we still need to be able to compute the steady state probabilities. And for that, we have looked at this in the last class. So basically what you look at is you look at a state J, and then from various states 1 to M, there is a way in which you can enter state J in one step. So this is called Pij. Okay, so this is P1J, and this will be PMJ. Okay, and if you look at the frequency interpretation, okay, the number of times you find yourself in state J is actually going to be equal to number of times you find yourself in state I, and then you make that transition. Similarly, you have to sum over all of these i's, and that is the interpretation that is given. So basically what you get is this equation, which is called as a balance equation. Pi j is equal to Pij into I should not write it this way. So you first find yourself in pi I, and from I you make the transition to Pij, and I going from 1 to M. Okay, so this is a system of equations. There will be one such equation for each of the states. Okay, so there, in this example, since there are M states, there will be M equations and M unknowns. So you would think that this is by itself enough, but unfortunately this system is not full rank. Okay, so its rank is n-1. So that means you need one more equation to be able to solve this, and that equation comes from the idea that steady state probabilities are probabilities. So when you sum that over all possible states, you should have they should sum to 1. So this two together is called balance equation. We can use this to estimate the steady state probabilities. So let us now look at an example to understand how these steady state probabilities are used. So consider the old example that we had studied in previous lectures. So there are two states with this state transition probability given here. So we had done the calculation that the steady state probability is given by this. Okay, and now let us say we are starting at state 1. Okay, so now given that you are at state 1, we would like to know what is the probability that at time 1 you are at 1. Okay, and you are also interested to know at time 100 you are at 1. Okay, so this is the question here. So that if you look at, so we can write this in this manner. So probability that you are in state 1 is basically you're at state 1, and then you remain in state 1 in the next time period. So time period starts at 0. So this will be P11. Okay, because from 0 in the next time period also you find yourself in 1. So this will be P11, and next one, that will be probability that you find x100 is equal to 1 given that at x1 you are at 1. Okay, so this is if you remember, this is called as the 99 step transition probability, R11 of 99. Okay, now for this particular Markov chain here, R11 of 99, since 99 is a large enough number, we can approximate this as pi 1. So this will approximately be equal to P11 is 0.5 times pi 1, which is 2 by 7. So let me just write it here to just make it very clear, but this is what that number will turn out to be. Okay, and similarly looking at this, so the first thing is R11 of 100. So starting from state 0, you and after 100 steps you are in 1. Okay, at state 0 also you are at at time 0 also you are at state 1. At 100 also you are at state 1. So that's why it is R11. In 100 steps you remain at 1, and then from 100 to 101 you go from 1 to 2. So this will be P12. Okay, so now this again we can approximate it as pi 1 times P12. P12 is 0.5. Okay, so we can do calculations like this when you have this. So now we can also ask questions like P100 equal to 1, okay, and x100 x200 is equal to 1. So something like this. So here again basically it will involve two steps things. So from state 0 in 100 steps you you will be at state 1. State 0 is at also 1. So this will be pi 1. Okay, and from 100 to 200, since there are large number of transitions, again the information that you are at 100 in 99 steps, it doesn't matter what the state at 100 was. So that again will be pi 1. So this will be pi 1 square. Okay, so this ways you can do the calculation. And now if you remember, like I was able to say that 99 is large enough, right? We said 99 is large enough, 100 is large enough. Okay, so how do we really understand that? How can we say that for sure? Okay, so the way to understand that is if you are at state 1, the chance that you may move to state 2, it can happen in roughly 2 time periods. Okay, so in 100 there will be enough number of transitions between the two, and there are number of ways in which the initial information can be lost. However, if you were to replace this with numbers like this, okay, so this something like this, 0.001, and this has 0.0998, and then this has 0.002. If we had numbers like this starting from state 1, roughly it will take, so basically from 1 to 2 the chance is 0.001. So this transition will take at least 1000 iterations. So 100 then is no longer enough to say that the mixing has happened. Okay, so basically the idea as to how many transition is required depends on the time scale of the Markov chain. Okay, the time scale being, you look at the exact probabilities and you find out how long does it take to make some type of transition. For this example, perhaps 100,000 is a better number, and this mixing is a well studied thing, but we will not go into more details in this class. Okay, so that's about this. So now let's look at a very interesting real life application. This is a problem that was studied by Erlang about 100 years ago. So Erlang's distribution, you have seen, this occurs in Poisson process. So time for kth arrival happens to be Erlang's distribution. So basically Erlang was looking at, he was at a time when telephone had taken off. People were able to talk to the outside world using telephone lines. Now the important problem there was, like, if you consider a village, okay, so within the village you can have enough lines so that people can talk to each other. So that really is not the problem. What is more interesting is you need to be able to set up parallel lines, to a major exchange so that you can reach the outside world. Okay, so these lines, if their number of them is B, that actually influences your cost. So higher B would imply higher costs. Okay. But lower B means a lot of dropped calls. Okay, so what can happen is if B is 10 and if 11 people attempt to make a call outside of this village, okay, then the one person is going to lose out. So he is not going to be able to use, and he will find that the system is in a busy state. Okay, so this is the problem essentially. And then what you can do is you can further estimate what is the rate at which new calls are being made. Okay, and that is assumed to be Poisson with rate lambda calls per minute. Okay, and further we can also assume that the call duration is exponentially distributed with parameter mu. So mu, again, the units of mu is going to be per minute itself. Okay, so this is the entire setup. You have a Poisson process where new calls are arriving at lambda per minute, and then you have the individual calls are lasting for up to mu per minute. Okay, and there are totally B lines available. Now if you really look at this, okay, so since the times at which the calls arrive, okay, that is not going to be discrete in any way, right? It can happen at any time. So this is actually lying in the field of continuous time Markov chain. Okay, but fortunately for us, and we can actually do a simplification. So basically what we will do is we will use the idea that we used to come up with the Poisson process itself. So what we did in the Poisson process derivation was that you took the entire time scale and you divided it into extremely small intervals of length delta. Okay, and then we said that probability that you get I number of arrivals at that delta, okay, is going to be, so for I equal to 1, this rate is going to be lambda delta. Okay, for I equal to 0, this will be 1 minus lambda delta. Okay, and we said that there is no way you will have more than 1 arrivals, because this delta is very small, right? So this is what we did. So like this, we will use the same assumption in the phone company problem. Okay, so here is how it goes. So either you can be in 0 state, which means there are absolutely no calls in the system, that the village is not making any calls in this state, or it can be one call going on, 2 calls. So let's say this will be I minus 1. Let me just clear this a little bit. So this will be I minus 1, and this is I, like this, B minus 1 and B. Okay, so this is how the system is. Now, since this Markov chain, what we have done is we have looked at the entire time scale divided into extremely small delta. Okay, and at any time, the probability that you are getting a new call will be lambda delta. So this is easy to see. Any upward transition will be lambda delta. Okay, the lower transition is going to be depending upon how many calls are there in the system. So in order to understand that, we said that every call lasts up to an exponential distribution with parameter mu. So if there are I calls that are simultaneously going on at a given time, so what happens is, you can think of that as a series of Poisson processes, I of them, okay, which are going on like this, with inter-arrival time being exponentially distributed with parameter mu, and then the state system moves from I to I minus 1. It will be essentially going to be a merged process. You combine all these processes and then look at the earliest time in which an arrival happens. Okay, and that we saw that happens is going to be the addition of all the Poisson processes being considered. Okay, so this is going to be, this combined process will be with a Poisson process with rate I mu. Okay, so as a result, the first call will happen with the rate I mu delta. So now what we are further making an assumption is that at a given time delta, there cannot be simultaneously either of these things will happen. Okay, nothing happens. So in a period delta, either one of the three things happen: nothing happens, no new calls are made, or the customer does not hang up. Okay, that's nothing happens. Or you can have one new call. Okay, or you can have one customer finishes a call. Okay, finishes a call. You can have these things, but you cannot have two of this. So you cannot have two new calls, you cannot have two customers finishing a call, or you cannot have one new call as well as one customer finishing a call. All these things simultaneously together will not happen. Okay, so I hope you are all convinced how these things are arriving, how these things are looking. Okay, so now with this we are now ready to study the steady states. Now one may wonder why steady state for this is important. So basically, if you are living in this village and then at a random time you place a call, okay, the chance that you will not find yourself outgoing line is the probability that the system is in B. So essentially pi B is the rate at which calls are going to be lost. Okay, so that is what we are interested to estimate. Okay, now for this problem, this has the resemblance to the birthdays process that we studied in the last lecture. So we can use the same idea. What we do is we make a cut here. Okay, and what we say is from pi I minus 1, you will go ahead to pi I. So this transition probability will be pi I minus 1 lambda delta. This has to be equal to the reverse one, so which is pi I into I mu delta. So we can cancel out the delta, and you are having this, you are going to have this kind of balance equation. All right. So you can actually do more of this. So if you actually simplify this, so we can write this as pi I is equal to lambda by I mu, okay, pi I minus 1, and then pi I minus 1 you can write it as lambda I mu. The pi I minus 1 itself you can write it as lambda by I minus 1 mu. Okay, so this way you can write it as I minus 2. So if you continue in this manner, you will get this equation, which is quite elegant. And then pi 0, we will use the idea that all the balance equations I equal to 1 to b, this has to sum to 1. So with that you can get even solution for pi 0. Okay, so this is now a complete representation of the system. Okay, so now we can use some back of the envelope calculations to see how this system will perform. For example, so let's choose lambda. So lambda, remember lambda is the arrival rate. Okay, so let us say the lambda is 30 per minute. Per minute, we will write it as this, and mu is 1/3 per minute. Okay, so basically an average call, so what that means is average call lasts about 3 minutes, right? Because an exponential distribution, the expectation of that is 1 over the rate. Okay, so that's why an average call lasts about 3 minutes, and there will be 30 calls per minute. Okay, so basically if you really look at this at a given time, you would expect 30 calls to be going on. Okay, and each of them being lasting for 3 minutes. Okay, so this number as I was saying, there is a lambda which is like arrival every minute, so that's about 30 arrivals per minute, and for a given time it will be this 30 calls will go on for 3 minutes. So on an average at a given time there will be 90 calls going on. So how do we really understand that? So let's say at time 0 the system starts, so there are 30 calls which are coming due to 0. Okay, and they will last for roughly 3 minutes, right? So 0 to 1, okay, so at the 0th minute and the 1st minute, so these are 3 minutes here. Okay, so let's just put these numbers. Okay, so this is due to the calls that are happening based on the 0th time interval. Okay, and now what happens in time 1? So at time 1 again you will have 30 calls of its own, and then they will last for intervals like this. Okay, and then for time 2, if I choose a different color, there will be another 30 calls that are arriving here, and not to mention at time 3 there will be another 30 calls which are arriving at time 3. So roughly at any given time there are 90 calls. So essentially a good good calculation, back of the envelope calculation for B is 90. But this has a problem, right? Because these are still random numbers, and this calculation is not really how it will be all the time. So sometimes there will be spillover to multiple states, sometimes it will be less states, and so on. Okay, so a more principled way is you look at pi b, okay, and then you set it to a certain desired system parameter. So let's say you set this, you don't want the system to be in this state. For less than 1% probability, you want the system to be at this state. So what you can do is you can look at this equation, you can put value of pi b, and then you can, so basically you look at pi b here, and then you set a value, and then you can design what value of b is suitable. So you can do a calculation like this, and yeah, so that's the way one can solve this. And in fact there used to be as Sitsikis says, there used to be engineers who have well tabulated calculation of these numbers, which they used to use to design actual telephone lines. Okay, so this is a very practical application. So let's move on. So in In Markov chains, there are various types of problems that one may need to solve. So one particular problem, let us look at this. So here there is a system like this. So if you look at this system, starting from 1, 2 and 3, okay, so these are all the transient classes, because either the system can move to state 5, after which it remains perpetually in 5, or it can go to state 4 and it remains perpetually at floor. So there are two recurrent classes here, okay, and then the system can either settle into this or it settle into this. And what we would like to know in a problem like this is, we would like to know what's the chance that the system settles in this recurrent class versus in this recurrent class. So that's the essential center question that we are looking at. So let us towards this, let us see how this computation can be done. So the way we do this is, we'll say that suppose we are interested in state 4. Okay, so this is what we are interested in. So we want to know what is the probability that the system enters into the state 4. Okay, so that we will denote as AI. So this is the probability that system settles into state 4 eventually. Okay, settles into 4. So excuse my spelling. Given that it starts at state I. Okay, so this is what we denote as AI. And now for this, so if you are at state 4 itself, probability that you settle into state 4, this is going to be 1. However, if you are at state 5, there is no way you are going to go to state 4. This is going to be 0. Okay, so basically, yeah, so the A4 is equal to 1, A5 is equal to 0. Okay, so but now we have to tell what is A1, A2 and A3. So that is a easy computation. So let us say we are in state 2. Okay, so you are in state 2. So with probability 0.2, you reach state 4. Okay, and from 2 you can go either to 3 with probability 0.3, or you can go to state 1 with probability 0. This is not correct. So this is not there. So from 2 you can go to state 1 with probability 0.8, or you can go to 4 with probability 0.2. Okay, so now from 1 to 4 there is some probability that this happens. This is we say this is A1, right? So now we are ready to state the actual equation. So A2, okay, so the probability that from 2 you go to 4 is equal to that you make the direct transition, which is 0.2, plus you make this transition via state 1. So this is 0.8 times you move the transition to state 4. So this is the equation that you can get. Similarly, you can get other equations. So in general, what you can do is you can write this common set of equations for every I in the system. Okay, so from state I you can go to state J. Okay, and then from there to reach the state of interest is going to be AJ. So this is the system of equations that you will get, and this happens to have unique solution. Okay, a variant of this problem will arise if you had instead of state 4, let us say there was and instead of this being a single state recurrent class, you could have a system like this, you know, where this could happen. This could be state. So this two forms a single recurrent class, and then now we want to know what's the probability that you reach this recurrent class. Okay, so we can have a system like this, and then there could be a transition to 6 and so on. Okay, so this could be a variation, but this is still the same problem, because if you are interested in this recurrent class, what's the probability that you get absorbed into this recurrent class, you can redraw this as a single node, and then you can then have these transition probabilities as before, and you can have the very same analysis with the new constructed node. So you combine these two states as a single state, and then appropriately redraw the transition probabilities, and then you can compute this using this system of equations to calculate what is the absorption probability. So now another question that can be asked is that you have a system like this, which is a bunch of transient classes, and then there is a recurrent class, and then starting at any state we would like to calculate the expected time till you eventually reach the single recurrent class, or it's called as absorption. What's the time that you require starting at a given state to reach essentially the absorption state or the single recurrent class state? So this, if you want to compute, so let us say for state I, we the probability expected time, we let's say we call it as mu I. Okay, so until reaching the absorbing state. So now mu I is equal to 0 for which? So if I am in state 4, okay, so this is true, right? So at state 4, what's the time, that number of transitions that you take to reach back at 4? Okay, so since you are already in 4, this probability is going to be 0. Okay, for others, if you are in state 1 or state 2, at least you need to make one transition. From 2, at least you need to make one transition. So let's look at 2. So mu 2 will be at least one transition. That transition could go to any of the other j states. Okay, so mu 2 to any of the other state j's. It includes 4 also, but it includes others also. Okay, so this will be mu 2 times 1 plus j equal to 1 to 4. Okay, p to j times, after j, how long does it take to reach 4, which is going to be mu j. Okay, so note that if you are going to take this path, okay, so this is going to be 0.2, okay, and then mu 4 is going to be 0. Okay, so that essentially drops off. So this is again, if you collect all of that, you will have n system of equations like this, and then there will be a unique solution for this system as well. So this is a desirable state. Okay, and again, the variants we can have, instead of a single absorbing state, you can have a bunch of absorbing states like this. You know, some with these probabilities could change a little bit. So you can have something like this, and then you can have transitions into this from other places, right? So something like this, and then we could ask what's the probability of absorption to this. And here again, what you can do is you can combine this into a single node, and then you can redraw the probabilities, and then you use this similar method to estimate this time for absorption. So look at it. So this first method was calculating the absorption probability. The second method is expected time to absorption. They have very similar structure. Okay, so it's a recursive structure, and the best way to like memorize these formulas is to really understand the mechanism, and which is really not that difficult. Okay, so I hope all of you will not memorize it, but you will actually understand it. So whenever you need it, you can pull it out. Okay. Another variant of this, you could have 2 recurrent classes. So from 3, you can perhaps reach 6, which is also a recurrent class. And then again, we can ask what is the time to absorption? What's the time till you eventually reach a recurrent class? So here again, what we will do is we will combine 6 with 4 and 5, write it as a single, combine that as a single node, and redraw all the transitions, and then we look at the time. Okay, so the original example that we studied is enough to really study all the variants of these problems. Okay, so I hope this idea is clear. So let us look at the next and the last set of problems around Markov chain. So this is called as the mean first passage and mean recurrent time calculations. Okay, so here the problem setup is there is a single recurrent class. Okay, so let's do that. So basically you have a single recurrent class like this. Yeah, some example like this where the system is continuously shuffling around. So the question here is there is a system like this. So let's say 2 is a special state. So, okay, so fix a recurrent state S. So let us say 2 is S. So this is the state S, and then starting from I or 1 in this case, what is the time that you start from I? What's the time till you first reach S? So this is the time that we would like to compute. Okay, So the quantity of interest is called as Ti. Okay, it's the minimum number of time that you take such that you reach the state S, given that you start at state I. Okay, so now Ts, which means the the first time till you reach S, starting from S, since n is, we are considering all n's greater or equal to 0. Okay, so even x0 itself is equal to S. So that way Ts is equal to 0. For others, it will be like from state I. Okay, you will at least need one transition to go somewhere. Okay, I is not equal to S, so at least one transition it takes to move somewhere. Plus, depending upon where you go, you reach some state J, and from there you will require Tj time. Okay, so this will be Ti. Okay, so what you are essentially doing is you are redrawing this Markov chain in this manner. Okay, so all the transition out of S you are removing. So here, suppose there was a transition like this, you are removing all those transition and making it self loop. You are only retaining transitions which go into S. So something like this, and then it reduces to the problem that we were looking before, and it essentially becomes what's the probability of absorption into S. Okay, so we are changing the Markov chain, redrawing it like this, and then it essentially drops down to the same problem that we studied before. Okay, and associated variant is mean recurrence time of S. Okay, so essentially what this problem, how is it different from the previous one? You are starting at state S. Okay, so that is also given to you. What's the number of time you return back to state S? Okay, so that's the question here. So you have to return back to S. Okay, and so from S you can go to any of the M states. Okay, and then with probability PS1. Okay, so this is where you probability that you go to state 1. Okay, and then this is probability that you go to state M, and then time to return back, right? This will be Tm. Okay, similarly this will be Tj, so on. So basically this is what we are calling as a recurrent time of S. So these concepts have a lot of applications, but many of this is beyond the scope for this course. But if you do read this in more formally, more in detail, you'll find that there are a lot of applications to each of these problems. Okay, so in summary, we looked at today several things. So we looked at we recap what was a conditions for having like a steady state probability. We looked at what is the meaning of mixing. Then we looked at the phone company problem. Basically, given a village, how many lines do you need to have out of the village? And then we looked at what's the probability that you get absorbed into a recurrent class from a transient class or any class in general. And then transient state or any state in general. And then we looked at expected time for absorption. We looked at mean first time passage and recurrent time. Okay, here this Tj is the same Tj that we had before. Okay, just to recap. So Ts star, remember, is the recurrent time starting from S. How long does it take to reach again S? Okay, so it moves to some other node and from there it comes back, right? So that Tj is the Tj that which is the first passage time. Okay, so that is all that is there in the third part of this Markov chain course. The Markov chain chapter. All right, thank you.